Video, I wanted to have a dialogue with you a little bit about the use of value objects within programming in general, but with a particular eye towards object-oriented programming. So from watching the video, help me understand. So what are some of the advantages that we secure when using value objects as opposed to objects that evolve over time, that mutate over time, change over time?
Can you share them?
Yeah, we can share them. So several larger scale data structures might be able to make use of common underlying shared representation, right? Why is it that sharing falls out automatically of value objects? Why do you gain the ability to share just because you have a value object? Yeah, someone else not going to go out and change it out from under you. I mean, in general, if something's totally under your control, you don't have to worry about it evolving much because presumably any evolution of it is something that you've deliberately chosen to undertake, right? And so you can evolve it as you see fit for your needs. But if something is shared with another party, maybe it's with code written by someone else, maybe it's in another area of your system that's only loosely coupled to your own, and whose rules and evolution you're not totally clear about. It's tough to share something with them because you might be counting on it being one way and they change it to be another way. So sharing comes out of use of value objects. As long as we know the situation as it is initially, we know it'll stay that way going forward. And that permits sharing. So when we talk about value objects, it's very natural for students who are earlier in their exposure to think they actually take more memory. More because each time you need to perform a computation with a value object, you need to produce a new one, right? You can't reuse the existing one. If you take two value objects and you need to combine them together and retrieve a third, rather than mutating one in place, you get a new one. But the fact is often we end up saving memory because we can reuse the underlying data structure. So that's one important benefit of a value object. And that benefit has some extra benefits that come along with it as well that we'll try to get to as well. So what's another benefit of a value object? Why use a value object? Yeah, okay, it's side effect free. Okay, what does that help with? Okay, the fact that it is side effect free, how does that help us? We don't have to worry about state. Okay, and worry is perhaps the key word there. It simplifies reasoning. It simplifies our understanding, and when we have code that's complex enough for whatever algorithm we're wanting to perform or what have you, often it adds a layer of kind of extra reasoning that we've got to trace back, okay, what is it that's touched this? What's last changed it? Where was this modified? And when we're looking at code, often we're scanning for sort of where was this variable last changed? It's got this weird value. Where did that come from? Could it have been changed at this area of the code and that area of the code? So reasoning is actually easier about things that are immutable. If a value is passed in to us as a parameter, as an argument to a function, to a method, and we've got this value circulating, this variable circulating in this method, if it has the wrong value, we know where to look. It's the value passed to us, right? The dependencies there are clear. And that makes it easier to reason about things. We can more easily trace where did this come from? Where did this value originate? And that simplifies our understanding when we're looking at code. What else does that ability to capture dependencies, where this thing came from, What last modified this thing, etc. What gave us the value for this thing? What else does that help besides reasoning? It's a very important thing that this helps in today's environment. It's one of the central motivators for performance advances within computer science right now. Is what? Concurrency. Sorry?
Concurrency?
Yeah, concurrency. So achieving concurrency, and particularly parallelism within this context. Concurrency, ladies and gentlemen, we could have two concurrent processes going on. They're both operating at the same time, but they're not, in fact, parallel in the sense that they're not both operating in tandem on two different execution units. But in many cases, we can secure parallelism at different levels. One way of securing parallelism is through our multiple cores, right? Multiple cores. Another way is through multiple distributed computers. Another way yet might be through GPUs on our machines, graphical processing units. And in today's world, when we're looking to secure additional speed-ups with our code, increasingly we don't look for so much serial speed-ups and how quickly we can undertake certain operations in succession. Rather, we look for opportunities for parallelism. There's a certain amount at a low level that can be secured through pipelining of instructions and so on processors. We can undertake successive steps within a given operation in parallel with other steps from other instructions. But really, a lot of the big games are between processing units, cores, machines, processing units on GPUs, etc. And one of the biggest challenges with undertaking those in the context of evolving objects is the dependencies are not clear. You can't tell what depends on what. Why is that so important for parallelism? Why are dependencies and clarity on dependencies really important for parallelism? Yeah.
Because it gets really complicated once one core is modifying something that another one might be reading, or you have to make that clear so that really odd Heisenberg.
Exactly. Ladies and gentlemen, I mean, if you've got two things that don't depend on each other at all, that evolve independently, that's what we call embarrassingly parallel. It's extremely easy to take those and have them run in parallel because we know one doesn't have to go first, and the other one uses the value from it or anything like that. They're in separate universes as far as we're concerned. They can just go and be put in parallel and operate. Whereas if you do have dependencies, if one depends on the other, on the intermediate results of the other, what have you, or the final result, we need to stage them. We need to have one go before the other, or have them go in a staggered way so that one produces results in the other and vice versa, or what have you. It's where we have dependencies that we need to coordinate, right? We have no dependencies. We don't have to coordinate. So, ladies and gentlemen, when it comes to parallelism, dependencies are where it's at in terms of limitations on parallelism. It's not the only limitation. I mean, there's limitations associated with number of computational units, but it's one of the central ones. And with languages that allow for evolution of objects, those dependencies become less clear. And if we go back to our very first little take-home exercises in this class, in a language like C, there be dragons. Why there be dragons? Why in a language like C is it difficult to automatically parallelize a lot of operations? Or let me put it another way, take you partway there. Why is it hard to get an effective understanding of dependencies in a language like C?
Is there references in plan?
Yeah, the references and pointers are so exposed. You could have a given variable. I mean, you could have a local variable in C. You could have a parameter in C that has a pointer to it. And that pointer can be passed around to other objects and to other function calls. They can be placed in data structures, written to global variables. And then someone somewhere, some function you call or whatever, writes through one of those things through that pointer. It dereferences that pointer, right? They have a pointer to your variable, and they write to it, and they change it, plus, right? They change it, they increment it. And see, I mean, you can have all sorts of things pointing to your data structures, to your variables, and through pointers, they can refer to them. Because you have pointers pointing to these things, it's hard to know, are they evolving out from under you? Is this variable still holding the same value it did up there? You know, maybe there's a variable, a local variable A right here, and you initialize it to be 1, right? And then you go and you're using A in some code. Maybe you never touch A, but if somewhere in your code there's a call, say, to something that has, this is an attempt at an ampersand, something that refers to the address of A, then it's escaped. And now who knows what refers to this guy? And nowhere in your call do you see anything that writes to this, but someone else may have gotten this pointer somewhere in your program, and now it's referring to A. And now it can frob A. Now it could change A. Now it can change out A from under you, and you don't know where it can, right? The dependency is not clear. Does this other code, F itself, does it write to A? Does it only read from A? And if now you've got a call to G, and maybe G calls a whole bunch of other things, or maybe there's some concurrent process going on that's updating Windows, and any time during this A can be modified. Those dependencies aren't clear. When you've got pointers passed around, you can have multiple pointers, P, Q, all pointing to, well, it could be pointing to A here, right? It could be pointing to this underlying variable in a way that you don't know. So here could have aliasing. You could have something that you know as A getting access through multiple pointers. Who knows where? Who knows at what time? It's not clear. So for a language like C, from the standpoint of parallelization, what you can eke out automatically in terms of parallelization from a compiler, it's pretty impoverished. Pretty hard to go parallelize things, to figure out automatically, oh, this can run on this processor, or that can run on that processor. Because the dependencies aren't fully clear there. And moreover, in a lot of our code, we're going to have issues with dependency management associated with changing state in terms of synchronizing things. And we'll come to that as our next topic today. Okay, so dependencies and dependency management are key to parallelism, to effective use of parallelism. And languages that make that clear, and constructs like value objects that don't evolve over time, make it easier to parallelize. Whether it's done automatically or manually, it's easier to be confident that we're going to secure value out of it. So that's good. How about another benefit for value objects? For an object that's immutable. Suppose going out of this class, you never write anything in a language except for JavaScript, or you never do anything except in Java. Would value objects still have a role? Yeah, I mean, those languages, you can very easily commonly support things that are not value objects, but they still have a role for many of these reasons. But one of their biggest roles is, as we talked about, serving as building blocks for larger data structures. So as I mentioned in the video, if you're building a data structure out of pieces, it's easier to use value objects. Why? Suppose it's an immutable data structure you're building. Why is it easier to build it out of immutable pieces?
You don't have to worry about changing them.
Yeah, you don't have to worry about them changing.
Oh, and I mean, related to the concurrency thing, you don't have to worry about the state of it changing in your working level processes.
That's right.
It might not be changed underneath you.
Exactly. So yes, it's not going to be changed out from underneath you when you're working across multiple processing units. So you've got this thing that's built out of these pieces that are reliable at some level and that you know aren't going to evolve. Okay, suppose you're building a data structure that's not immutable. It's in fact mutable. It's something that is going to change. It is evolving state in this higher level structure. And I want to build it out of pieces. Is it going to simplify it to build it out of mutable pieces always?
You can control access better.
Yeah, you could control access better with immutable pieces. That's not to say you want to build all pieces of it out of immutable pieces. No, I mean you need at least some pieces to be changing. But just because you're trying to build something that's mutable, that can evolve over time, doesn't mean you won't necessarily want all the pieces to evolve over the time. And Andrew used the key idea there. Look, I mean, if you're building this thing out of these pieces, you need some degree of control over what's going on. Yeah, you want this thing to evolve, but you want it to evolve in well-defined ways. And if you're building it out of mutable things, mutable objects, you still need to be careful in terms of how you reason about and limit the degree of that mutability, how those objects can evolve over time. You don't want them to evolve willy-nilly and who knows what sort of way. You want them to evolve in a well-defined way that you control. And if you've got these internal objects which are made out of pieces that can be changed, you have to exercise control. And what's one of the biggest ways we exercise control? If we have things within us that are mutable, what's one of the biggest ways we have to exercise care about those things? What do?
There's like public and private access.
Okay, good, public and private access. And if we return a value that's a reference to one of those things that's mutable, what do we have to do? Copy it. So if we hand out a reference to this internal thing, we make a copy of it. If we take in a reference to something that's immutable externally and we want to use that information internally, we often need to make a copy of that. Because the reference we have to this external thing, someone else may have that same reference. It may change it out from under us. So we have to make a copy so it doesn't change out from under us. We want to refer to that information, but we have to refer to a copy of that information, right? So when we're building mutable data structures, we want to be able to reason about them in a clear way and to have them not change out from under us. And because of that, it does take extra degree of care if we're building them out of mutable pieces. If we want to build immutable data structures, that especially is the case, and building things out of immutable things is easier. So if you're building an immutable thing, building out of immutable pieces is easier. If you're building a mutable thing, building out of immutable pieces for at least large parts of it simplifies your reasoning, lessens your worries. Immutability, ladies and gentlemen, immutability, regardless of whether you're using a language that is standardly supports, standardly has a common paradigm of using mutable things or not, immutability gives you lots of benefits. Okay? It simplifies reason. And if you're writing things in a language like Java, and you go to create an object, rather than just thinking that it's interchangeable whether you have it be an immutable object or you just, you in other words, you have an immutable object where you have a constructor that builds it, and after that it's immutable. You don't want to think that that's somehow 6 of one, half dozen of the other with a situation where we build it using constructors and then we do setters to set the things inside of it. Those are very different things. And a lot of students in our undergrad program here, I found, seem to think of them as more or less equal in terms of strategies. You build the object and then you set its fields versus you, at the time of constructing it, you use the constructor to build it and it's immutable after that. Those are very different things. Very different things in terms of the ease of reasoning and building things out of that object, etc., and the mistakes that can be made. So the latter of them, not building the object initially and then just using it as an immutable object, but instead using setters to set things, depending on those setters to be set properly, it's a lot more complicated to reason about. So if you're never doing anything except in languages like JavaScript or Java where mutability is kind of the standard, but the default paradigm, think about immutability. Think about using immutable objects. They'll help you in a lot of cases. Okay? And in many other languages like Scala, you will find immutability to be an attractive option, and use immutability when there's well-defined reasons that call you to do so. Value objects. Any questions about value objects? Any questions? Yes.
I was thinking that wouldn't immutable objects would be a good case to consider where you are building a state-based components
Yep.
which can flow, where you can flow the immutable object through a specific component flow or something.
That's right. That's right. So that's a fairly common common need. And indeed, there's certain sort of patterns that come up in different contexts where either it very clearly you want something that's immutable or you want something alternatively that's mutable. For other patterns. An evolving state pattern is very commonly achieved with some elements that have got to be mutable, but you've got to ask yourself, in terms of evolving state, is this an underlying object that's being changed over time, indeed, or is it captured by having an object that at any one time has one value, but over time you produce successive versions of that object that in fact are not using the same underlying memory, but instead are just being produced as full sort of copies with slight modifications. And how feasible it is to do one versus the other will change a lot. And over your course of time as software engineers, you're going to find challenges where increasingly the compiler will help something that's basically an immutable data structure in all the ways of reasoning about it effectively act as performant as something that's mutable under the covers, and it's actually represented in a mutable way. An example here would be, we'll actually see an example in what's probably the next take-home exercise, where we'll be taking Conway's Game of Life, where we've had these two mutable data structures, A and B, right? These sort of two buffers. And at any one time, you're updating A or you're updating B. You're reading from B and updating A. You're reading from A and updating B. You're mutating them. They're mutable data structures. We'll see that that could also be described in a perfectly functional fashion, where you're taking the current data structure, A, and you are processing it and yielding a new data structure, B, that hasn't actually it hasn't underneath the covers mutated in your implementation, mutated A, but rather it's produced as a result. Just like we add two values together, 1 plus 2, and we get a third, 3, without changing 1 or 2, right? And when we do that, a sophisticated compiler may recognize that, oh, yes, but in the end, all you don't actually need to you allocate every time a new copy of this giant two-dimensional array. You could simply reuse the last one and just go between two of them. A really good compiler, down the line might be able to recognize that. And indeed, good compilers for functional languages do recognize opportunities for reuse of memory rather than allocating something new every time. So even something like a mutable, a situation where we have evolving state, doesn't necessarily mean that under the covers there's lots and lots of repeated allocation going on if it's captured in a functional way. You may be able to capture it functionally. That is, when you change something, you're not changing it in place, but you're making a copy with that change in it, and yet be able to do so in a very memory performant way. Compilers for functional languages are designed to realize opportunities for sharing and reuse. Yeah. Okay, other questions? Good. Okay. I appreciate the chance to have that discussion, and I value the fact that you